this PageRank, this probability transition matrix P, and this has all of the links in all of the web. So the good news is it's probably not that much bigger than 1 billion. Something like an average web page has like 20 links. Okay, so so P may be something like maybe this only has 20 billion non-zeros. Okay, so these are entries where it doesn't have a link. So it's still mainly going to be zeros. It's going to be much sparser than this. But still, it's 20 billion of these. Okay, and each of them has to store the address of another one of these entries. So there are ways you can do some compression on here, but you need to store, a value between 1 and 1 billion, basically, for each of these entries. Okay, so I don't want to store all these on one machine. So even doing one of these steps, and I only have to do like 50 of them, is going to require a lot of space. So I'm going to spread that out across these machines. Okay, so now the question is, how do we want to store these across these different machines? What is the right way to do this? So, and let's not think about the key value pairs first. So let's not worry about that. I'll tell you how you can think of this with key value pairs a little bit later. There's usually an easy way to get there. How would you store this if you wanted to kind of just do one step of this in parallel?
Pretty simple idea. I don't know if it's right, but maybe just have everything having to do with one page. Like if a page of a row, you're going to want to have like everything having to do with that page on a certain machine. And that machine can have like, I don't know, 50 million, 500 million pages, like 500 million rows.
Yeah, so if you look at this, and we think of this as the random surfer model. Say the random surfer model is at B, so he's this guy surfing the web. He's at B. He's going to, if I look at this matrix, I only need to worry about this column associated with node B here. I only need to look at these guys, and I said each web page roughly, on average, has only 20 links on it. So for this surfer, where he is now, I only need to store this one column. Right? So maybe I can break up the web in terms of columns. Okay, so the way to think about this matrix P, actually, conceptually, I usually like to think of it as a big rectangle. Okay, and so this is my matrix P, and so my input vector here, this is going to be Qi, and my output vector is like this. So actually, let's not worry about this part here. We just really need to worry about this step. This part we can always we can add this on. This is just doing this output, shrinking it by a little bit, and then adding something to everything. Okay, so the really hard part is here. And so this will be the output Qi plus 1. And so I kind of go through this process where I'm at this node here. I go the corresponding column, and for each one of the things where it has some entry, I spit out and I add something into this corresponding block. Okay? So, if I can think about, for each of these things in Qi, I only need to look at this part of the matrix. So if I want to break this up into k pieces, one way to do it is think, I'm going to break this up into what's called k stripes of the matrix. Right? So I'm going to have so this is called these k stripes. It's called striping. I like to think of them as strips, but they're called striping the matrix. So I guess it's like painting stripes. You know, if you paint stripes on a car, then it's going to go faster, right? So it's the same thing with the matrix. It may not actually be true with cars, but I've never tested that. And then if you're dealing with this vector here, if I'm dealing with this stripe on one computer, I only need this same part of this input vector as well. So I can stripe this vector as well. So I'm going to have between 1 to up to these k different stripes. And now I can break it up. So I want each of these stripes stored on one computer, and this computer just has to process each of these things. Okay? All right, so now, so this is kind of the first general approach. And this is going to work okay, but we're going to improve on it in a second. But let's see how we would do this in MapReduce. And we'll talk about it under the kind of the pure MapReduce, and then we'll say how you would probably do it in a way that makes a little bit more sense, because that's kind of cheating. Okay, so first of all, I need to get these as key value pairs somehow. And the key thing with the key value pairs is I start with the data, which is this matrix. So this matrix, I don't need to store all the zeros. I only need to store the non-zero entries. Okay, storing all the zeros would be ridiculous. That's a billion times a billion, right? I only need to want to store something like 20 billion non-zeros. Okay, so that means that's a Pij. So that's going to be the ith starting point and the jth output point. So that would be some cell here. So this might be ij. Right. So I can store this with, for instance, one way of storing this would be ij as the key, and then the value would be the probability transitioning here. So maybe there were 10 links on web page I, so this would be 1/10. Okay, so maybe this is how it's initially stored on the server. Okay. And then I have this matrix Qi, and so I want to say that this is also part of the matrix, so this should also be part of the identifying part, which is the key. Right, so this key may be ij, and it also has something that says, or so it says, like some label M says this is from the matrix. Okay. And then I also need to store this internally, and so I could say that I only need to store one entry. I could store this is going to be, this is value I, and this is from the vector. This is my key. And then it stores some value there. Maybe this was 0.007, right? So it's some current probability of being on this page, if you're, okay? So now I need to start from here. This is my input to the map. And I need to get this to the reduce step. Okay? So what do I want to do on the reduce step? So my output, the output that I want is just going to be this vector, right? The values of this vector. And they can be distributed. So I need to get the value for each I of this vector, right? So how do I translate this into MapReduce? So what I need to do, if I want to, I need to take the value stored in here, that was this QIV value, and I need to multiply it by here, and then I need to get it out to this guy somewhere. Okay, so these are the parts. I take the value stored here, I multiply it, or if I look at this one, I take the value stored here, I multiply it times all of the non-zeros. Each of them gets out here, I need to aggregate these.
So what is V?
The V is just saying that this is, I need to say, this key tells me what is stored here, right? It's from this vector. I've used vector and matrix, right? So I could say, this is the PageRank vector that I'm storing. Well, I just put a V there. Okay, and this is stored as being part of the matrix. So I somehow need to get some of these things into one place so I can add them all. So what's the first thing I need? So how PageRank, how MapReduce works is it takes data which is distributed in a way that I don't necessarily have control over, and I need to bring the data I need to compute a function together on into one place. So how would I do this? How would I get, the first thing I need to do is I need to get this value and I need to have it in the same machine as each of these non-zero entries here. Yeah?
So why not map the I values and in Pij the I values, all of them together?
Yeah, good. Right. So what I can do in the map step is I'm going to get this to a key value pair that just has I, and then it'll store with it J and 110, just coming from the matrix. And this one will also, and maybe it has some code that says this is coming from the matrix, so I know what this is. And I don't need to store the I in the value because it's already in the key. Okay, and then for this, I also need to store I, and now I have this 0.0007, and saying is coming from the vector. Okay, so this was the map step. Once I have the map step, then I have everything for the same column on the same machine after I run the shuffle. Okay? So then in the shuffle phase, so then in the reduce phase, so my input to the reduce phase is going to be some value I, and so it's going to have a bunch of these different values, and they're not all going to be the same, right? So some of them are going to be value J, 110, and M. Right? I may have another one that has the J prime is going to be 1 out of 9, and it's going to be M. And then I'm going to have this, and then I'm going to have this thing from the vector, which is going to be 0.0007, and saying that this is from the vector. Okay, so this is my input on one reducer in the reduce step. Okay, and so then I'm going to convert this into a couple of key value pairs. Each of these is going to need to get sent out. So I'm going to have this one here represents this one of the values, the value here, and each of these other things that get sent out is going to be one of the other values I have in my set. Right, so the output to here is going to be, now I need to accumulate on these values J. So it's going to be J, so for instance, J will be 110 times 0.0007. But I'm also going to do this same thing for J prime. And J prime is going to have 1/9 times 0.0007. Okay, so I'm going to output this set of these key value pairs. Okay, so I still haven't gotten I still haven't gotten the output part here yet. What I've done is for each of, now I need to think of it as I've split this in the other direction. Now I've got this row. All of this row needs to map here. Everything that was pointing to this web page has produced a key value pair where the key is j. So that means in order to get them here, I need to run another round of MapReduce. This was the end of this reduce phase, but now I've gotten them in some way that, actually here I don't have to do the shuffle phase anymore. I can run another, I don't do the map phase, I have to run another shuffle phase, and this will give me all the things with the same key j will be on the same machine, and then I can add up these values. Right, so this was map number 1, this was reduce number 1, and so now I can kind of skip map number 2. This is empty. This I didn't do anything. I just ran the shuffle phase with the keys j that I got out of reduce number 1. And so then on reduce number 1, on reduce number 2, my input is going to be j, the key j which corresponds to this row, and all the values associated here are going to be v1, v2, up to vk, where there were k things that linked onto this web page j. And so then the output here, which is essentially going to be qi plus 1 of j, is going to be the sum of vi. I just sum up these values. Okay, so does this kind of make sense how this worked? Do you see how you got from this data here, stored abstractly into this set here? So now I could write this back out actually as the key value pair. Now this was j, but this was actually this sum is actually going to be sum of these VIs, and say that this was the jth entry of the vector. So now after I've done this, I've gotten this value of my distribution vector after one step. And so actually this might not be the right quantity. Instead of doing this sum here, I would do beta times I times the sum plus 1 minus beta times 1 over n. Right, so if I do this distribution step, I just add this in here in this last step. Instead of doing a regular aggregate, I do this kind of aggregate with this extra term. So actually, if you remember back to kind of doing the like ridge regression at lasso, this term is actually somehow regularizing the solution as well. There's some kind of cool connections there. So you kind of see this is how I move this data in the same way here. So I needed to use 2 steps with MapReduce here. I needed to do 2 rounds here, and I said I should try and avoid doing rounds because they kind of have some overhead to it. So I do one map, which gives me everything from the matrix into some form and pushes this on here, and then I do a reduce to tell me which row it corresponds to, and then I just add things up from the row. I couldn't do this here because I didn't have all the data associated with row J on the same machine at this point. This machine only had all the data associated with column I instead. Okay, so what would I do? So in practice, they would not do this in 2 rounds. They would get this computation done in only 1 round here. Okay, so how would I do this in 1 round? What's kind of the point? What's kind of the wasted step here? So are people? I'm not getting a lot of feedback. So are people confused as to how is working as this kind of, this magical MapReduce beast. I've specified these couple of simple things, and it somehow automatically computes something. Is that really confusing, or is it really easy? I'm not sensing, or are you all exhausted from finishing the project and don't know what I'm talking about? Okay, all right, so we need to liven it up a little bit. Okay. So I'll just kind of cut to the chase here a bit. So instead of, what's happening here is every time I do this map step, I'm going from all the parts of this matrix, which are indexed by I, and I'm doing a shuffle phase where I move them onto some sort of reducer indexed by I, and then I don't do anything with them again. This shuffle step in between the mapper and the reducer does the same thing every time I do it. It's kind of moving it onto the node indexed by I. So I don't really want to move this data to the same location every time. So I kind of think of storing the matrix in this stripe on the same machine. So I can assume that all the data is already stored, all the data associated with column I is already stored on some mapper I. So this is kind of breaking the most abstract model of MapReduce. But this is kind of a simplification. Then the kind of the main idea here is you want to bring the computation onto the data, not move the data as little as possible. And so the mapping is trying to allow you to not move very much data, just kind of simplify things first. And so what you'll do is instead you'll think of keeping this whole stripe on one machine, and that starts at the mapper. So then the mapper will also, let's say I've intelligently been able to get this QI onto the machine out. Okay, so now I said this may have been stored in multiple different locations. Well, this part of QI is going to be smaller than this whole stripe probably. So I can probably store this QI part on this machine as well. There's some expensive part after each reducer where I write stuff back to disk, and so I can choose to write it onto this part of the disk that has this same part of this same part of the stripe here. Okay, so if I do this, I can do this computation in only one round. Okay, so then what I can say instead so then the input to the mapper is going to be these keys, where it's going to have key I, M, so this is from the matrix, and it's going to then have all of the values in this stripe. Right? So it's going to have J110, M, it's going to have J prime, 1/9, M, and so forth. So it's going to have this. It's also going to have key I of the vector. And here it's going to store, so it's just going to store like this value coming into this vector. Okay, so I'm going to have these on the same machine starting out as the map phase. Okay? And then what I did in this reduce, I can do in the map phase. Right? I can combine together these different things. As everything on the same stripe, I can convert. So I have all this information in this stripe. Now I want to convert it into the things that I send to this along this row. Right? So then the output here is going to be some value j, which tells me which row, let's call this row j. And so I'm just going to output the 1/10 times 0.0007. So this is going to be one key value pair I output. The other one is going to be row J prime. It's going to be 1/9 times 0.0007. Right, so this will be the output of the map phase. Right, and then in reduce phase, I just need to do the same reducer here. So then in this reduce phase, I can already have everything associated with this value j, all these values which came in along this row j here, they're now all on this one machine. And I can add them up, multiply them by beta, and add this 1 minus beta times 1 over n factorial. And so that's the whole iteration here. So if I don't have to move this row here, then I can do this in one round of MapReduce. Okay. So am I done now? So is this how they would do this? Is there going to be a problem here? Okay, so, yeah.
There needs to be many iterations for this, right? There needs to be many iterations for this, right?
Yeah, so I'm going to run this step. So the start of the step, I started with the vector qi, and I got qi plus 1, and I repeat this some number of times. Right? So 50 times is usually enough. Usually, I don't have to start with some random thing here. I start with the result from last night, and it's a pretty good guess. So after, at most 50 iterations, I'm going to converge pretty quickly to the right, towards the right value. Yeah, so I'll need to run this some number of iterations. So really, this factor of 2 in the number of rounds really went from 50 calls from 100 calls. From 100 to 50 calls of this, so it's going to be a very big difference. Okay, so the problem with this is going to be this reduce step. Something's bad about this. Something's not right about this. Well, it's correct. It's correct, but something's really slow about this reduce step. So what does this reduce step correspond to? So I said that, and also there's some similar issue with this map step. I said on average, say each web page has 20 links. So that means on average every column has 20 of these things. And you can work out the probability. It means that on average, every page is going to have 20 pages linked into it, right? But there could be a really high variance here, right? Some pages are really popular, the ones with high PageRank likely, and that means a lot of people link to them, right? So, a lot of people will link to Hacker News. It's going to be a very popular website. So let's say, maybe it's not unreasonable that 1 million people link to Hacker News. So that means that this step here, where I'm adding up all of these values, I'm going to need to add up 1 million of these values. Whereas for the other ones, I'm going to need to add up like 20. So this step for the row J corresponding to Hacker News is going to take a lot longer to run than all the other rows. So I don't want this imbalance. I want to kind of not have to kind of have this imbalance between the different tasks. So I talked about the curse of the last reducer. The last reducer to finish really tells you when you can start up again. I can't really do the next round until I know what's going to happen with this row J, because that row J will correspond here, and then that's other things are going to be waiting for this one to happen. So I had a similar problem when I was doing the word count, where the word the occurred like 7% of times, right? So what did I do to get around this? Well, it's good to see that at least you are all working very hard on the project. So, I guess this would have been a bad day to have a quiz that was graded. Okay, so what did I do with the word the? I even mentioned it at the start of the lecture.
With the combiner.
That's right, yeah. So I use the combiner. So before I send everything in the shuffle step, I combine together all the instances of the word the, so say for that document, right? So how would I do something similar here? So think of, I've got this stripe, and before I send it off, I want to combine stuff together. How would I do that? Yeah, that's right. So basically every time you see this thing where it's just aggregating, it's just summing here, I can pre-process this sum before I send it off. So in this example here, I'm looking at just one column here, but this stripe, I'm only doing k of these stripes for each kind of, essentially it's more than for each machine, because you're going to have many maps where you do, every HDFS block per machine. But you're going to have multiple of these columns in each of these stripes. Right? So for each of the columns, I can look, if two things point to the same page here, I can aggregate them before I send them. And then if I only have k of these stripes, this sum can only be over k different things. Right? So that means that I can do a combiner where what I'm going to do is for row J, I'm going to have V1, V2. I'm going to get a single thing here, which is the sum. Okay. And so I didn't want to do all this extra step where I had to do this taxation, or where I do this redistribution with the beta. I'll still get the same sum here. I've added some stuff up before, and then I add them all together, and then I multiply by this beta term. Okay, so I save this part for in the reducer. I just aggregate these things in the sum. So if I do this combiner, it's going to improve this. Okay. So this is going to help a lot, but I'm actually going to have a lot of these stripes. You shouldn't think of these stripes as the number of machines I have, because in order to get a little bit better load balancing, I'm going to say let's put maybe 10 or even 20 stripes like on each machine. Because I don't really know how big these are going to be. Maybe I can kind of learn over time. But things may change, so I kind of want to do 10 or 20 per machine and do each of them individually. And then I'm going to have some replication. If one machine gets slow, I can redistribute its work. I don't have to do all the work of that one machine. All right, so I'm not going to have more stripes than I have machines. So I may be running on like on 10,000, 100,000 machines. So this sum, this final sum here may still be like 50,000 things or something, right? So it's not going to be too bad, but I haven't reduced it. Maybe it wasn't 2 million, but it's now 50,000. I'd still like to make this even smaller. So how could I how can I make this smaller without having any more memory for each of the essentially HDFS blocks. So each of these stripes should be like one of these blocks that I have in the distributed file system. So how can I make this aggregation in this combiner be more effective with the same size blocks? So I want to be able to add together more things with the same size block.
Use tiling instead of strips?
Yeah, right. So if you haven't heard of tiling, I'll explain this. So there's multiple ways to kind of break up a matrix into pieces, right? So I've got this big rectangle again, which is my matrix P, and the striping was these vertical strips. But that's not always the best way to do this. In a lot of kind of large-scale matrix computation, you actually want to break the matrix up into kind of these tiles, which are going to be these sub-rectangles instead. So instead of having a full column, you may break it up into these tiles, these blocks, these rectangular blocks. Okay? So now I can essentially use the same algorithm for every one of the tile. So now I still have, let's see, I still have this input vector, which is qi, and this output vector qi plus 1. Now this output vector, or this input vector, is broken into fewer pieces. So this, I don't know, maybe this seems like that's better. And then each of these tiles, you can think of being outputted here. Now these are not going to, these ways they're broken up is not going to be quite as helpful. Okay, so now for each of the tiles which is associated with the value I, this corresponds with the column in here. Right, so for each of these, I want to then send it over to one of these blocks. Okay, so